Hello, everyone. Welcome to one more episode of our podcast, Real AI Now. Today, I'm very excited. We have a very special guest, Jared Stanley. Jared is the CEO of Adinkra, robotics, engineering, AI, computer vision company. We know each other. We used to work together in the past, Jared. I understand you have a master's in applied physics and some education also in machine learning, as far as I know. And well, we worked together in the past. But since then, a lot of things happened, and you founded Adinkra. I'm sure we'll have the chance to talk about that. So welcome, Jared.
Thanks, Paulo. Thank you for having me, and excited to be here.
So can we talk a bit about your background as a physicist and what inspired you to start working on AI?
Sure. Yeah, I became a physicist because I wanted to understand how the world works, right? And I think that physics is all about figuring out the structure and the interactions of the world. But there's a great number of problems in physics, from a practical standpoint, that really can't be solved with kind of a closed form simple equation, or maybe the equation, but it's kind of intractable computationally or for different reasons. And so I started getting excited about AI as a solution to those kinds of problems. And kind of as a specific example, when I was in grad school, we were trying to figure out these kind of chemical structures of perovskites, which is a new type of solar cell, and it's just intractable to generate all of these crystals and figure out exactly how they're all going to work and do all these optimizations. And that's where I started getting exposed to AI as a solution to that problem. And fast forward to today, and you have folks at like DeepMind, folding these proteins and doing this with AI. And so yeah.
So let me just try to understand. So what fascinated you about AI was that you could use AI, in this particular case, machine learning. You could use that to explain the universe, sort of.
Yeah, I mean,
or you could use it as a tool that helps you kind of describe or explain or model the universe.
There are people now using AI. They're actually using some computer vision techniques and others to actually derive physical equations from video and motion. So, I mean, yes,
that's
potentially. But I think
reverse engineering the nature using using a brute force, almost brute force kind of AI technique, just observing, and then kind of. But how is that really? That gets us to the topic of how explainable is that? How understandable that model is once it's built. But I would like to put a pin on that and get back to your background. So you mentioned physics. Physics uses an analytical way of explaining the world, or at least it classically does that. You saw AI as a tool to explain things that cannot be explained very easily using analytical models or quantum physics or whatever.
Right. There's this concept of, and neural networks actually satisfy this property. There's this concept of universality, that you can use neural networks or similar systems to sort of approximate functions to arbitrary precision. And I think that if you kind of think about, here's an image, detect if it's a cat or not, it's very, very hard to write a simple equation, a rule-based sort of equation, in the same way that you might for two bodies attracting each other gravitationally. Like, there's a lot of different kinds of cats. This is a very, very hard thing to put into closed form. But with AI, you have a method of approximating a cat function, if you will, and it can generalize to detect and understand that that part of the world. And this is very, very high dimensional data, right? This is not
Okay.
just two bodies interacting. This is,
Mhm.
maybe millions of pixels that have to be understood and interpreted. And so
Mhm.
I started getting interested in the types of problems that were like that, in that there either wasn't a well-defined kind of equation that you could get to, or there were so many parameters that
Mhm.
it was just intractable to write some sort of rule-based system. And I
Okay.
think that's where AI became a really interesting tool for understanding the universe.
Okay. I actually have a link to that. I used to work for an observatory. I was at an observatory for 7 years, and one of the teams that worked very close to us was the image processing team, if you will. So they built image processing software for cameras, and among other things, so some of the software they did was about detecting objects in images. So you had like very large images of the sky, pictures of the sky, and you had like thousands of objects in those pictures. And they developed these algorithms, I mean, really real algorithms to detect each type of object. And they held all these rules, like, so they looked at, I don't know, this is a like a star, or this is a galaxy or a quasar or whatever. They had like an algorithm that described what properties that need to have, and kind of to classify that as an object. And of course, if they use machine learning, they could have just taken a few pictures and started like labeling them, okay, and saying this is a star, this is a galaxy, this is a quasar, this is a galaxy cluster, this is this and that, and then just have machine learning learning it, instead
Right.
of trying to come up with formulas and rules to detect those objects. Does that make sense?
Yeah, and it's not like those rules aren't there, but I think that AI gives us a tool to kind of compress what is actually a very large amount of data and sort of automatically figure out what is important, right? And I think that's what's interesting about it, is that we could sit down and define all of the contours and features and things that make a
Or
quasar
cat.
a quasar or a cat. Yeah, we
Yeah.
can, right? If you look at the inner layers of like a convolutional neural network, you'll start to see some of these primitives that can be combined. But I think that what's interesting is that it's really a powerful tool for automating this process. And this universality concept says, you can kind of learn these representations in a way that you can approximate a cat or a quasar, and you don't need to write the rule-based system. And you
Yeah.
guys do a lot with natural language processing. Sure, Google used to have an extremely large script to do language translation. Like, this was an extremely large rule-based process, and now it's a couple lines of code, because
Yeah, it's a
you
model
have
now. It's a
the model
transformer now.
now, the transformer underlying it, exactly.
Uh,
And so you now have something that has just compressed all of that information. It has decided what's important, for that translation process, which of course varies depending on the languages you're translating between. But that's what I think is really powerful about AI.
So trying to translate this, what you said, to a less technical audience. Or basically expressing it in in different words. What you're saying is that classically in physics, but also in computing and mathematics, you looked at the phenomena or something in the universe or in the world, and you try to come up with a formula or an equation or something from mathematics that describe what you see, right? Or a set of rules, set of equations, set of formulas. And this works quite well for, I don't know, for Newtonian physics. This works beautifully. Even for relativity, this works, sort of, up to a certain point. Now, but in many cases, you're just overdoing it because you have to. It's a complex thing. Now, if you use machine learning instead, you can actually compress that knowledge into something much, much smaller, because you can have just the machine learning by observing what the rules actually are, and that comes up sometimes with a representation of that same knowledge you already had, much more compressed. That's what you meant, right? So
Yeah,
that's one point. And the
yeah,
other point is that there are phenomena that we cannot explain at all, right? That we don't know how to explain, but actually that machine learning, or if it maybe not explained, but we cannot model, let's say, we cannot create a model of certain phenomena, certain systems, certain things, but actually you can put machine learning system looking at it, and it can actually model it, right? And this is the groundbreaking thing, isn't it?
yeah, I think so. And I keep returning to this example of this cat or these stars. And I think that if you if you kind of look at that question, it's very different than saying, how do two bodies interact, through gravity, right? It's not, the question itself is sort of ill-posed in the sense that there is no analytical model of what a cat is. Like, this is a concept that we have.
Mhm.
And so the only way forward in those kinds of problems is to develop an algorithm that can kind of model that concept. And I think if you look at, things that are happening today in self-driving, for example, like driving cars, it's the same idea where there is no analytical model of like how one should behave on the road. You have to be adaptive. You have to take in all this input. You might see things you've never seen before, and you need to react to them. And so I think that's where, maybe AI isn't necessarily the right tool for getting at analytical physics-based models, but it is the right tool for handling kind of real world, high dimensional situations.
Right.
That's where I see it being really powerful. And so, yeah, I think there's a lot of examples of that.
So, how did you make the decision of, so stepping a bit back of the AI again, the topic, we get back to that, getting back to you a bit, how did you decide to start a company, right? How did that idea start? And why did you start a company, right? And how was that decision process?
Yeah, I dabbled with entrepreneurs and startups all throughout university. I had exposure to a lot of really inspiring friends and ideas. But at one startup I was working at, I was actually living in Zambia at the time, before grad school, and I had met this guy there who told me this story about, he had basically taken some off-the-shelf parts and had built an attachment for cell phones. And this, off-the-shelf kind of device was used to detect diseases in the eye a little bit earlier than was previously possible. So you could take
Wow.
this smartphone, you could detect these diseases in the eye, and the result of this thing getting deployed was.
So what was it, detecting eye disease, or was it detecting diseases by looking at the eye?
I think it was detecting a specific type of degeneration in the
Okay.
eye. I can't remember the exact kind, but the result was that this product was going, had already been kind of piloted and had saved, hundreds of thousands of people from, having these diseases. Like, they could preemptively detect this.
Okay.
And this was a huge shift for me personally, because I realized that, having an equation, of describing, I don't know, how the universe works, it isn't really the full picture. Like, sometimes you can take off the shelf things, combine them, and then create these tools that massively improve people's lives.
So this is why I wanted to start your own company.
Yes, I mean, I felt, and that's the same concept we have at Adinkra, is how do we accelerate the innovation and impact, associated with these kind of cutting edge products. I think that this really shifted my thinking in terms of what a business can do for society, because people come to us with these ideas, and they're really powerful. And sometimes you need, to develop a new algorithm, but often you can take some of the kind of latest and greatest tools that are out there, combine them in a new way, and solve these really important problems.
So let's talk about Adinkra then. So what does your company do? What is your mission, and what is, tell me about cool stuff that you do.
Sure. We're focused on robotics and AI, but our mission is to accelerate the impact of these technologies. We want to, have these technologies be deployed in the real world and making positive changes.
Yeah.
And what we really focus on is accelerating product development. So people will come to us with either ideas or products that they have, maybe a prototype for, and we really help them develop that into what it can become, add additional functionality, maybe design things from the ground up. But it's really about accelerating robotics and AI development.
Could you give an example of what customers come to you with?
Yeah, I mean, we've done some, autonomy projects. I think one project that was really interesting was in the construction space, and it was about, safety in construction, right? So these are, large pieces of construction equipment. They wanted to create, situational awareness for how this thing is moving in its environment, making sure it's not, creating safety risks for people, making sure it's aware of what's happening, and then building, a monitoring system to enable that. And I think that, that was an example of, you can use computer vision, you can use some technologies, networking technologies, to create an environment that is more responsive than human and actually prevent a lot of people from getting injured or killed in these kinds of construction environments. So that's an example of, a product that we helped build that has clear impact, like clear positive impact for the world. But, we could use kind of a combination of off-the-shelf components, as well as maybe some more cutting edge components that made that product more competitive in the market.
So could we dig a bit deeper in that project? So could you maybe describe for the audience what are the building blocks of such a product?
Yeah,
So
I mean,
you've got a drone, right? I understood that correctly?
In this one, we didn't use a drone,
Okay.
but we do have some fun drone projects I can talk about as well.
Okay. I mean, as you wish. So in this particular project, but you have computer vision, so you're observing the environment. How the cameras?
Yeah. We've done, linear sensors, cameras, LiDAR. In this particular project, it was all stereo depth based. So we were able to get a depth map of the environment, as well as RGB or visual information. And in terms of the major components, I mean, one of the first things you have to do is map the environment. You have to know, where am I at? What is around me? Not only what obstacles are around me, but what is the meaning of those obstacles? Like if I detect a person, how is that person moving? What's their trajectory over time? What are they likely to be doing? And so being able to have that kind of situational awareness, that map, that's one of the first components of the system. And you achieve that with, a variety of sensors networked together. You transform all that data into the same kind of frame of reference, so that you can build that map. And then ultimately you need to have some sort of system that can process that and make decisions. So you've got to have some sort of compute hardware, maybe some sort of application for human in the loop operation, where someone can kind of set certain triggers or, be in the loop monitoring a situation. You might even have autonomous capabilities where the human's out of the loop and the system itself is making those decisions. So yeah, I would say, sensors, networking, computes, always power is an issue.
Okay.
And
so is there some sort of agent involved that runs on a loop and has to kind of make decisions using a sort of a loop, or how does that work?
Yeah, I mean,
or does it get just triggered by events around it?
Yeah, in this particular project, it was more of a monitoring application. So the only real action that could be taken was to kind of halt the equipment so that it doesn't, do something dangerous. But yeah, in kind of more advanced behavior systems, you would see these kind of designed as agents that can fully make a larger range of actions. So for autonomous vehicles or autonomous drones, for example, these robots are making a lot more decisions autonomously. They're yeah, getting that data fed in and then using that behavior system to do that.
Okay. So maybe we can talk a bit about a cool drone project. So what have you done with drones?
Well, I can't go into too much detail about specific projects, but I can say that one of the things we're doing with drones is designing autonomous behaviors, and
Mhm.
autonomy is kind of this buzzword. So I think one thing that's important for folks to understand is that autonomy is not a binary kind of thing. It's not like you have an autonomous system or you don't. It's really this kind of long-tailed distribution of capabilities. Over time, the system is able to do more and more on its own.
Okay.
And there's this concept of kind of the human in the loop during that
Mhm.
process. But
So
yeah, go ahead.
if we cannot talk about particular cases, let me, for example, talk about a hypothetical one. So let's say you're building a drone that flies over some fields and for agricultural fields where you have corn, let's say, and it's trying to detect things. It's basically looking for dry areas that need more water than others. It's looking for maybe some infested areas with some kind of disease. So, I mean, how would the drone like that look like? So I'm assuming you need to have the drone itself. It needs to be able to fly, right? Maybe it has some kind of flight plan that you upload, and it kind of it knows where to fly, and it has sensors, right? So it starts flying around, has cameras. Let's assume it's just the cameras for now. It has cameras that look around. And then at some point, it needs to kind of make the decisions. And if we simplify this, and all the decisions it needs to make is, okay, there is a dry area over there, and report that. There is some disease over there, and report this kind of thing. So, and those are the simple decisions it needs to make. It detects a problem, it communicates that, reports that to some central. So how does that work? I mean, could you explain could we break it down a bit just for the audience to understand how such a system works?
Yeah, I think where you started is actually a really good starting point. So that kind of mission upload, right? This is kind of the specification of where is that field, how fast am I allowed to fly? How high am I allowed to fly, or low, right? And I think that specifying that mission is one of the most important aspects of,
Mission, okay.
yeah, like with the mission or the kind of task at hand. It's very important to specify that correctly.
Okay.
You also brought up this idea of it kind of flying around, and in robotics, we might call that navigation or path planning. And
Okay.
for a simple kind of rectangular field, maybe it's just this lawnmower pattern that the drone is kind of going through it. But you can imagine for more complex environments like coffee farms, where they're shaded by these trees and there's these other obstacles around, that path planning problem actually is quite significant. So having a way of developing kind of an intelligent, efficient path, before the drone even lifts off, is a really important aspect of these systems.
Okay. And how much AI is in there? Or is this not AI?
Well, I guess it kind of, most of these systems are optimization problems. They're not as much about the AI. They're more about, how do I optimize the coverage of an area with the minimum flight time or something like this.
A bit like Google Maps. I want to go from point A to point B, and I need to cover these spots in between, and I sort of calculate the path,
right.
the optimal path. Okay.
But there are systems that are, there are kind of AI variants of this, mainly with reinforcement learning, where these systems are actually learning more complex behavioral policies about how to accomplish something. So let's say you have a field that's, really, really big and you can't possibly cover it. And so you're maybe looking for certain cues to, like a dry area, to go check on something you care about. Or another application we've seen is, I live in Colorado, so there's a lot of these forest fires, right? And so kind of making decisions about how to
that's a
hone
good application, right?
Right. So there's definitely AI that can't, there's definitely ways you can use AI to kind of optimize the decision-making process for certain tasks. But yeah, I mean, at its basic form, it's really this optimization, right, for the navigation piece.
So you've got the flight plan or the mission plan uploaded. So the drone now knows where to go and knows how to get there, or at least it knows how to calculate how to get there. Now that we discussed, that's not really AI yet, or at least it's not machine learning, definitely. Or at least in this basic form, it's not. Then what about when you, so it has a camera and it detects that there is a dry area. How does it do that?
Right. So
that's computer vision, right? That's what I'm getting at.
Yes. Yeah. Right. So a lot of times what will happen is you'll have some sort of RGB sensor. You might have thermal sensors or other kinds of sensors as well, which is kind of one of the nice parts about computer vision is you don't have to be limited to just the visible spectrum from humans. But yeah, you bring in the sensor data and then you have some sort of algorithm on the back end that has been trained to detect this kind of situation. So it might say, these crops are really dry, or they're damaged, or there's pests or some other kind of indicator, disease maybe, that they can say this area is an area of interest. This is an area that we want to go investigate and maybe, quantify what's the extent of the damage, what's the severity of the damage, for example.
Okay. So you said two different things. I'd like to dig a bit deeper. Two things that I think are interesting. One is, so you have to kind of train the system to learn how to identify those, let's say, dry patches. Let's call them like that. And so you need to have data, right, to do that, right? So you need, and that's one thing. And this is data science, machine learning, and you can train a model, and you can. And then the drone can use it, and that takes me to the second part. Now, how does the drone use that, and where does that live? You said that the model is in the back end, but is it in the drone? Is it embedded in the drone software, or is it in the cloud, and how does that work?
Well, on the second part of that, like where is the model living? We've seen it kind of both ways, but a lot of times, and I think where people are trying to head is they're trying to push these models to the edge, more or less.
So in the drone itself.
Into the drone, exactly. Because that drone typically needs to make real-time decisions about its environment. One example is like delivery drones, right, which are being pushed forward pretty heavily. If a person runs into the path of that drone or where something's being delivered, you need to be able to react to that in real time. And often you can't achieve that with just the cloud, or you might not have a reliable, connection to the internet. So the system needs to be able to do those kinds of things real time. For agriculture, I think that, maybe you could push some of the processing to the cloud. So maybe the goal of the drone is just to sort of collect data about that, and then you can do some more advanced batch processing later. But certainly if you're reacting in real time and trying to, I don't know, explore the extent of some damage, or investigate something that isn't really known, then you do need to have the ability to make those decisions in real time.
Okay. This reminds me of something. Forest fires, right? I am from Portugal, and in Portugal, forest fires are a big problem. Are there drones patrolling forests already and detecting forest fires? Do you know of that? Because that's what I asked myself. Why can't we just have drones patrolling the forests, and you'd see the fires very early?
Yeah. It's a good question. I think, I've definitely seen some companies doing this and trying to do this. I've also seen drones being used to inspect kind of the propensity of a fire, right? So you're looking for where, how much
for prevention, actually.
Right. So they're kind of trying to survey or take stock of what's the actual risk in an area. And in
Yeah.
some of those cases, you can't really achieve that with like satellite imagery, right? Because there's a
Yeah.
lot of stuff underneath the canopy, or maybe there's stuff that's occluded that you want to kind of investigate. So I've definitely seen a few applications of that. I've also seen people not using drones and really just setting up cameras to do this monitoring, right? And you can kind of imagine a camera looking over a large area and detecting smoke or detecting something early like that. Could also be used for this purpose.
Yeah, good point. Maybe that's simpler and maybe cheaper also. So you could install in theory like every few kilometers or miles, like cameras that kind of watch what's happening, and you don't need drones for that. That's a good point. Might be more practical than drones.
Yeah, and I think there's kind of this general thing with drones too, where sometimes it's easier to do things with satellite data or these sort of like these kind of static monitoring systems. So it's finding the applications for why do I need this thing that can actually fly around, right? So if I'm thinking about utilities, like we were talking about fires, utilities actually end up being a pretty big factor in fires because some of their equipment gets outdated, or they need to kind of check that it's up to date, and it's a large cause of fires. So one idea is, okay, let's go look at the forest, but another might be, hey, let's look at the equipment that could start those fires. And for that kind of work, drones tend to be really important because you do need to get really close. You need to build these 3D models of the grid. You might be detecting specific defects or problems, and then you might want to convey that to the inspectors, the operators, to say, hey, these assets need to be updated or handled. And so you can actually get at the fire problem in a kind of a different way as well. And I think that's where some of the best applications for drones are, is in some of that inspection and surveying work, actually.
Okay, so maybe enough with drones. Even though drones are really cool, I would speak about drones the whole day. But so in robotics, and so other than drones, and what other cool things is your company doing?
Yeah, while we're pretty young, and we're focused a lot on drones. We've also done some stuff with autonomous vehicles and equipment, as I've mentioned.
Yeah.
But I think one of the other areas that we're kind of focused in is this idea of like simulation, right? So how do you build kind of a digital twin, if you will, of your robot sim? And then how do you verify that the behaviors and actions and operation of that robot are safe and meeting your performance standards and physically realistic? So, let's say we have a computer vision algorithm, we want to test it, we want to test that the drone or some other robot can actually respond to that appropriately. Then you need to build a kind of photorealistic physics-based world, and then you need to test all of these things in simulation. And that's one of the areas that we're really investing in a lot. And simulation is complementary to real world data, but it's a really great way to get started with research and development, because you don't want to be spending, you don't want to be breaking things in the real world or causing harm to people. Those kinds of things can be very dangerous and expensive. So simulation has a nice, it's a nice way of kind of validating a lot of your software and development process along the way.
So, okay, yeah, that makes sense. Simulation. So in the simulation, I'm thinking of, so you simulate the 3D world, and then you have your own drone simulator that moves in that virtual world and kind of behaves. You test the behavior of the robot in that virtual world. This is what you mean by simulation here. Okay.
Yeah.
And how do you
imagine kind of a video game, right? A really realistic video game, but instead of some sort of zombie game, you're trying to inspect something, and you can throw wind in there, you can throw physics in there, you can build customized PID controllers for how you're going to control the robot in that real world.
This is a whole world.
Yeah.
So are there things like that? Are there good tools out there to to create those simulated environments so that you can test a virtual drone in them? Is that
Yeah, there are a lot of really great tools, and there's a lot of
okay?
good, two qualities. One of the qualities you really need in a good simulator is a physics engine, right? And there's
Yeah.
a lot of great physics engines out there that can kind of do that. There's a lot of approaches to sort of estimating some of those physics, right? If you're trying to do like flight simulation, or you're trying to do different kinds of mechanical aspects for your system. So that, yeah, certainly there's a lot out there. I would say that there's also a lot of work now being done in kind of how do you generate things for that world? How do you script
Mhm.
agents and sort of scenarios? And so the kind of number of assets and things that you can build and the ease to build those worlds is getting better, every day.
Okay.
There's a lot of really cool tools out there for that.
What's the connection between that and the metaverse? Is there a connection? Is there similar technology?
Yeah, I
What's
mean,
it?
I think a lot of the tools that are being used to build these worlds are directly applicable to concepts in the metaverse and how we're designing worlds there, right?
Mhm.
So, and I think that also, we kind of talked about human in the loop and missions, but virtual reality, augmented reality, these are all also quite important for how do you kind of control and understand these systems, and how do you kind of
Mhm.
put a human in the loop effectively for these kinds of
Mhm.
systems. So yeah, I think there is a lot of crossover in concepts there.
Okay. I was talking the other day. So there are two things that come to my mind right now. One is around um, like self-driving cars and autonomous driving, and the other one is about, well, I forgot now. Let's stick to the first one. So I was watching a talk the other day about autonomous driving, and the person, the speaker, was saying that humans are highly underestimated as drivers, and they are incredible drivers. And the numbers I don't remember. It was, I don't know how many million miles human drove in on average until they had an accident, right? So this was kind of the what I took from that conversation. So and obviously the controversy with autonomous driving is that it's very hard to match human performance, right? Do you think that's gonna happen in the next foreseeable future, or will we have to compromise at some point and say, okay, we accept that cars are terrible at this, or robots are terrible at this, but we do accept the risk and we still see the advantages?
Yeah, it's a really interesting question, and I know a lot of people have opinions on this.
Yeah. What
I
is your
think that
opinion? That's what I'm interested in here.
I mean, I think that I'll kind of break this into two different things. One is in structured environments with really well-known parameters like construction sites. I think you're going to see very,
Mhm.
very successful deployment of autonomy because
Yeah.
you have ultimately lower dimensional things that can happen. Like there are certain rules. There's not as much
Mhm.
variety. And so those are problems that tend to be a little bit easier. And I
Mhm.
think you're also seeing this in the logistics space with all these mobile robots, right? Like
Right.
autonomy
And
flourishes in those kinds of environments where it's very
also
structured.
we just had a few weeks ago a podcast cast here, Roland Becker from Just Add AI, and Just Add AI, they have a system, a software system that helps tram drivers. So driving a tram is basically it's on the tracks all the time, so it's the dimensionality. I mean, there's a lot less dimensions than driving a car. So I can see that their autonomous driving can excel, can really work well.
Absolutely. I think structured, kind of more controlled environments, we're going to see a lot of value added. And we're kind of saying like, oh, there's just this one track, but these problems are not really trivial either. I mean, there's a lot of
No, they're
engineering
not.
and sensor development. And I mean, this is not easy to do by
No.
any means. But I think that where the second part of your question is kind of in this generalized autonomy where how do you build a system that can kind of react to the true variety of the real world? And that's something that, never say never, but it is hard for me to imagine, it's hard for me to imagine how fast we can get there because of that variety. Like, and I'm gonna kind of talk through maybe one example, but like if I see a person on the sidewalk, right, and I'm driving and they have a dog, an autonomous system today, they might be able to kind of predict the trajectory of those things. They might even be able to, they probably will be able to classify it at this point and kind of make some predictions about it. But there's a lot of additional context those systems don't process today. Like we would know, for example, that the dog is on a leash. We'd be able to say, how big is that dog? Is it likely to, drag the owner into the street or not? What's the behavior of a dog versus a human? What's kind of the expected thing that those people would do, right? So we kind of have all this context about
humans are incredible.
Right. And so like not only do we detect it and classify it and estimate its trajectory, but we also know a lot about humans and dogs. And I'm not, I'm not sure how much that's relevant for the task of driving on roads. Certainly for highways, this is not super relevant, but there are a lot of cases like this where we apply that context to actually effectively do things like driving, right? Like, can I make the yellow light? I know the yellow light's always a little bit longer, right? Like there's just so many things like that I think we will get there, but it's a much harder problem.
Wouldn't it just be easier to let the computers drive? So if all cars are driven by computers, then, and they're all connected somehow, all cars know where the other cars are, and it makes things a lot simpler. At least we remove one of the largely unpredictable factors, which is other humans. And if you remove them all, everything becomes much simpler. Okay, there's still there's still people walking on the street and animals crossing the street, and that's not going to go away. But there's no other drivers. Basically, there's just computers.
Well, you bring up an interesting point. We were talking to folks in the transportation department recently, and like, one of the things they're doing is they're sort of optimizing for public transportation, how buses move through cities and this kind of stuff, right? So I think that, and there's these platforms like CV2X from Qualcomm and that are kind of connecting all these things, right? So it's even as you incrementally get there, not everyone needs to be connected, but even as you start to build in some of that intelligence, you can start monitoring those traffic patterns, you can start monitoring behaviors or unsafe systems. You can actually already add a lot of value, for example, in this traffic example on throughput, right? Throughput or safety. So I think that like where AI and maybe these computer vision technologies is really going to shine is even an incremental deployment in part of the fleet or in the public transportation can add a huge amount of value to people's lives. But you are right that it is going to take time to kind of get everyone onto that system. There's always going to be some fractions of different standards that people are using, and it is going to be a challenge to kind of get everyone aligned on that. But I wouldn't say it's a prerequisite for adding all this value, but I would say that it's certainly a barrier to adoption. It makes it harder when some people are doing something completely different.
So it's a lot. It's more about making sure that people understand. Okay, this is not a general AI. This is an AI that is good at this one thing, and it's done by the others. It doesn't need to know anything about anything else. It's just does this, and it does it very well. So I mean, probably that's a good start if you start doing that. So I just reminded the other thing. You talked about logistics, right? And one of the things I heard was, let's say you have like a warehouse and you have a robot that kind of picks up things. I mean, Amazon has this kind of stuff, like fulfills orders, goes and picks up whatever it is, it needs to bring it somewhere else. And now these robots often share the environment with humans, right? And I hear that this is a challenge, right? To make an environment where robots move around sort of freely, and this could be drones or could be other types of robots share the space with humans, right? I mean, typically, I don't know, car assembly line, you have robots there. Humans don't go where the robots are because it's dangerous, right? And now when you try to bring robots to share the same physical space with humans, how advanced is that technology? Does this work well, or it's still very dangerous?
Yeah, I mean, so a lot of these warehouses, is my understanding is that they're set up sort of in this partial way. The robots are kind of on one side of a fence doing a bunch of different functions, and then the humans are kind of working collaboratively with them at some interface, or in some limited cases, they're working
But
alongside
they
each
don't.
other.
Okay, they work
Yeah,
alongside already. Okay.
I think in some cases they are, but by and large, it's sort of this segmented, right? These segmented worlds where the robots are really operating on a handful of tasks that they're really good at in a safer, more structured environment, and then humans are kind of taking on these less structured tasks. But I think that this is where people kind of use this buzzword of autonomy in kind of a strong way, because I think when people say autonomy, what they're kind of imagining is a system that can kind of do all of these functions without a human. But in reality, it's this long tail distribution. And I think a more appropriate word in a lot of these cases is automation. And the scope of
Yeah.
what can be automated, right? The scope of what a robot can reliably do every single day is getting better and better and better. But humans are incredible. We can do a very, very large scope of things. And so it is just going to take time, not only for us to build trust in those systems, but also to design them in a safe way where we kind of get to this threshold that we're going to say they're really, truly autonomous. And I think, kind of going back to the drone example, because we work so much on drones, certainly some behaviors can be automated, right? And the drone can make those decisions. And so some people might say that's autonomy. And certainly flying in the air tends to be a little bit easier than a city street, right? So there's a lot of autonomy. But in reality, I think humans are going to be on the loop for quite a while, and it's going to take time to build trust in these systems and really define what's within scope and what's out of scope.
Okay. What's the biggest challenge? So, okay, robotics is too broad. There's obviously lots of challenges there, but if we look at computer vision, right? What is the biggest challenge right now in computer vision? What is computer vision not good at the moment? Not good at all. And yeah, and how do you see that evolving?
Yeah, I really see like a few areas that are kind of needing improvement. I mean, one is hardware. Just having compute. I mean, the human eye is like 576 megapixels. I think it's estimated to be. Like, the amount of data that we can process in real time is unbelievable. So I think having hardware that can kind of make those computations and understand that data, that's something that's, again, getting better every day. But there's a very wide gap between what we're able to do and what this hardware can do right now. I think another answer that people would say is,
so if you compare the hardware that you have available now with the biological eye, what eye would that be? Of a fly, or of a what is it worse than a fly?
but I don't know how it compares to a fly, but your iPhone maybe is 12 megapixels, right? And the eye of a human is 576. So it's
okay.
I would, maybe even a fly is having more data, right? So
Yeah.
I think that just we have to recognize that the human brain is extremely efficient at this, and that's a challenge, building hardware that can kind of process that data. Right. To say nothing of, that's kind of the compute side, but also the hardware itself, like how fast can we get that data? How much resolution is there? How do we fuse different kinds of data together? So I think a lot of advancements in hardware are necessary to kind of continuously improve that area.
So you think that the only limitation is really the computing power, the hardware, or is there some new science and machine learning and new AI that is needed to actually reach something close to human performance in terms of computer vision?
I mean, there's already, right, like LiDAR and other systems, like they can compute depth more accurately than a human already, right? So
Mhm.
I don't think that these systems are necessarily less performant than a human in all cases, but they
Mhm.
are hardware limitations, and especially the compute and power requirements. Those are something that the human brain is just very, very good at. And so as we start to kind of ingest more data and kind of build these more accurate, maps
Mhm.
or scenes or whatever, we definitely need to solve those problems. I know for drones, for example, one of the problems we've run into a lot is you really need a very bulky, capable drone in order to kind of move, to have LiDAR. You need a lot of power for LiDAR. And
Mhm.
so vision systems are a lot more compelling for a drone use case because you get a lot more data with a cheaper, payload weight, cheaper power requirements. But um, the hardware just it requires a lot to get some of this data.
So, so what you're saying is that I'm trying to translate that to layman's terms. So, what you're saying is that the hardware well, the science, we have the science, we know how to do it, but we just don't have, in terms of physical or in terms of computing power, we just don't have the computing power to do that yet. All right.
Well, there's two other major challenges.
So we have the computing power, but it's still too expensive. You need large machines to do something similar what the human eye would do
Right, right.
at the same speed and the processing of the amount of data. So we know how to do it. We have some physical limitations. So we need to develop some new, more efficient technology to surpass those physical limitations. Is that what you mean?
Well, I think hardware is one part of it. I would say there's kind of two other areas that immediately come to my mind. One is the amount of data that's available. And then I would actually push back on the fact that we have the science. I don't know if the nice thing about neural networks are they're these universal approximators, but I wouldn't say that we've solved kind of general intelligence or that we have the right algorithms yet. So
No, I was just talking about computer vision, just like identifying objects, for example, or depth, or this kind of things.
yeah,
Not general intelligence, no.
well, I think data is another area that your algorithm can only, but see, this is what I kind of mean by the right algorithm, right? Like humans,
Mhm.
for example, we can kind of invariantly detect objects. We're not training on 10,000 vases, 10,000 coffee mugs. Like we're not doing that. So there are some like structural architectural problems on the models and how we approach those
Mhm.
kind of things. And the kind of idea that we can just train this
Right.
object detection system on millions of different types of classes, I think isn't necessarily the right approach. The human brain is doing something a little bit different. And so there's this
Most
common
likely, yeah.
problem. There's a common problem in computer vision, right, with brittleness. I just saw something on LinkedIn the other day where
Mhm.
someone was wearing a really confusing sweater and the people detection algorithm wasn't picking them up. And
Okay.
you can imagine in a self-driving case, there's these attacks that they have to worry about. Like what if someone's got a stop sign that they're carrying around, right? And this comes back to context. Like the human brain says that's a stop sign being carried around. That's not a real thing. But
Right.
the algorithm might think, oh, that is a stop sign. I better stop, right?
Right.
And so I do think that there's brittleness in the algorithms themselves, and then
Yeah.
there's also the data challenge. How do you build systems that can allow you to annotate faster automatically? We've done this work together where you're
Mhm.
prioritizing kind of the least confident cases, but the data challenge is always a big one. And I think that there's different ways to look at this problem, but if you have not the right algorithm, probably you're going to need more data. And so if kind of all three of these things can improve, you get the right algorithm, better data labeling, and then better hardware to capture more high quality
Mhm.
data. I think that if those three things can really advance, and they are advancing, but I think that's where we're going to see a lot of improvements. Those are really the big challenges I would say today in kind of these systems.
Okay. So yeah, what is the next big thing then that's going to happen in this area? So I mean, we uh, like companies like deep organizations like DeepMind, OpenAI, Meta AI, all these like there's like a race, mostly among the big tech companies, but also companies like Tesla and all, they're all contributing to this race. So all kinds of things are coming, like you talked about protein folding, but there's also like multimodal large models that can, I don't know, they can chat, they can talk, they can play games, and they can make decisions to do stuff. They can draw pictures, they can compose music, all in one single model, stuff like that. So where do you see this going in terms of if we focus on computer vision, what's the next big thing, or what is the next big breakthrough we will need that will happen next?
Yeah, there's a lot happening in computer vision.
Yeah. Or what are you looking forward to? I mean, what are you waiting, like in hoping that happens, that you think will be the next game changer?
Well, I think that one of the areas we've kind of touched on this idea of like a universal approximator, right? I think we're building these tools that can solve a wide class of problems, right? You kind of alluded to this, that the same model can be used for multiple cases. Mm-hmm. That kind of generalization is really, really powerful, because it's telling us that something about the architecture, something about the model itself is actually kind of a generalized solution to a large set of problems. It's not necessarily just about the data that you're giving it. It's not necessarily even about the task. There's something else there. And I think I'm really excited for seeing these systems become a little bit less brittle and a little bit more generalized. I'm not sure that we've quite solved that yet, but with AlphaFold, for example, and some of these things DeepMind is doing, I mean, the same kinds of structures are being used to solve a wider and wider variety of problems. And we're now running into the data limit, right? How much data can we capture? And hopefully that process becomes more efficient as our algorithms get better. But I think that, what really excites me about, especially in robotics, is reinforcement learning and some of these more generalized solutions to behaviors, or to kind of interpreting that data. And I know that's a little bit different than computer vision, but computer vision is a very big part of bringing in that data, compressing it into something usable for those systems. But I think that generalization is something that seems to be accelerating, and is, I don't know if it's one breakthrough or many, but specifically for robotics and control systems, the ability to build a generalized behavior system, right? Okay. Training that in a simulator, showing that this thing can kind of react in a very robust way to different kinds of situations, that is very, very exciting to me. And I think computer vision is a fundamental part of that, because so much of the world, so much of the data we interpret is vision-based.
So do you think that transformers will take over convolutional neural networks?
I think so. Yeah.
Okay. Because I also read about that, and they're taking over everything.
But I try to ask myself what's fundamentally going on there. But I think ultimately it's a more powerful architecture for relating data over long distances, right? Like when you're working with these like RNNs and stuff, it's very short-term kind of memory. But really, I think the fundamental thing with a transformer is you're able to somehow persist and kind of relate data over longer, that's in completely different areas of an image or completely different areas of a text. And that to kind of go back to my point, like that kind of concept, I think, is where these breakthroughs are going to come from, is that we're able to solve some of those kinds of problems.
All right. Thank you, Jared. I think we ran out of time. Thank you very much for joining us. I think we should do this again in the future. There was I had lots of fun with the conversation. Thank you for listening and watching. Don't forget to like this episode, and to follow our podcast on Apple Podcasts or Google Podcasts or Spotify. Thanks again. Thank you for listening, and stay tuned for our next episode.
Thank you, Paulo. It was a pleasure.
Thanks,
Bye.
Jared.